Hello, welcome back. So let's see if the sound, I've been having a few problems with this lately, but it should be working right now. I'm just gonna actually just log in on my phone just to double check that everything is okay. There, everything seems fine. Right, so okay, let's start again. Welcome back. So this is extremely open science. We are right now going to be picking up where we left off last week, which is okay. All right, sorry, the echo, at least I know the sound's working. I just checked it on my phone. So, all right, so we're picking up where we left off last week. So let's start from the beginning. Our goal here is to see if we can turn this intuition or this observation that genomes with some indels or an excess of indels have a lot of broken genes, which leads to a lot of parent pseudogenes, so short genes that are short interrupted. And we've been doing this by looking at simulated genomes, where we take genomes that are supposedly high quality because they come from genome databases. When we started with a handful of very top hits of microbiology, E. coli, Bacillus subtilis, and those types of big players. And we added, using actually a very simplistic model, we added some mutations, and now we saw that yes, indeed, as we add mutations, we have more and more small genes at average gene size, and then the question is how, what really is a small gene? So if you have a gene that's 300 amino acids, is that small? And so the initial idea was, okay, let's normalize by the KEGG orthologous group it belongs to, and then go use the GMGC, so the Global Microbial Gene Catalog, as a reference. So this is what we did so far. It seems to work okay, but we only had a handful of examples, and so last week we slightly expanded those examples, and here I showed this not on the stream but on the recap. So this is our score right now. Probably not going to be the last version. Sum of Z scores below -4, so it's a negative number. It's a negative number that goes, and and here the dashed lines represent the unmutated version, so supposedly the high quality, and we can use these unmutated versions to set the threshold, right? So if, for example, here -500, none of the real unmutated ones is anywhere near -500, and so -500, that's probably really bad. -1,000 is awful, right? Okay, but this is still 1, 2, 3, 4, 5, 6, 7, 8, right? Yes, and so what we did last week is we downloaded everything from Progenomes v3, everything being the representative genes. Representative genomes, right? So let's work with that today. So, okay, let's see if I can spell. All right, so I'm here at the data directory, and okay, everything was downloaded, and in particular, the representatives FASTA is the unzip file. And where is it? There it is. Okay, so great. And it's a bzip too, which is very, I think by now qualifies as a little bit old-fashioned, but it's nice to see. Nothing wrong with being old-fashioned. All right, so here it is. So let's play around a little bit. Okay, so this is the code we had, and now what we would like to do ideally is change this simulation code to run on every single genome there. So let's just do a little bit of exploration. Data. Okay, so I think Okay, this is going to fail, but let's just do this. Let's just check the headers. So if I vaguely recall this, these two elements should be the ID that I'm looking for. And then this is the config ID. So and while that's running, I also want to look a little bit at. So the problem with this is that this is not going to scale. Right? So we're spending. So for E. coli, this is a bit too much, and also the. Yep. So there are two issues here. So one is it's just a lot. So if we are now, so we can do a bit of math. So let's say that's 400 M times 40,000. So M times K equals G, and so we have we have 1.6 T. So so we're gonna need in the terabytes of disk space, not ridiculous, but still a lot. All right. So can we do a little bit? So we're good. So that's one problem. The other problem is frankly that this was going to be this was starting to be slow because we were parsing these files all the time. So this here, let's look. So we have all of these protein files, which are all more or less redundant anyway. And then we have the diamond outputs, which is a TSV. So let's explore this a little bit. So we can explore a couple of things here. So one is diamond output. How would this look if I just gzip this? Okay, we can get a pretty good. So that's one. So we can probably get pretty good compression here. So the protein files, we actually don't need all of this. So later we use the protein files only. Let me fix something on NeoVim. We all use the protein files only to get these headers, which is, first of all, it's a little bit slow because we're opening up these thousands of files and going through, all of them. And then in the end, all we get are these things. So instead of doing it this way, can we do it the other way? Right, or in the sense, can we do it? So run checkm2, and then can we do it as a post-processing step for checkm2? That's basically my question. Checkm2. Okay, let's do it this way. Okay. Okay, so we would have something like this. Gene positions. So what I want to do is more like this. I want to move this here. So this gets the gene positions from a single FASTA file. Okay, so no, that's not it. It's the okay, so something like this. Something like this. Okay, something like this could work. So something. So here, so right now I'm just trying to. Okay, actually this could work. So get all gene positions. So this is a task generator, and so here import regular expressions there, sort all of them, and then someone was telling me the other day that the biggest problem with polars as opposed to pandas is that all of these, you know, tools like Copilot, etc., they all like pandas, and they keep recommending pandas code. All right, so this would work. Does this work? Yeah. Okay, sorry, this is something. Is this correct? How is this possible? All right, I'm a little. This seems more reasonable. Yeah, it seems a bit more reasonable. Okay, I was some screw up there. Okay. Yeah, this is kind of terrible. Or not kind of terrible, but this is not great because this is not 100% safe. It's possible that things will get a little bit messed up. So basically, the problem is what happens if there's an interruption right here. This is not 100% safe. As not sure I really want to. Not sure I really want. Yep. So a lot of what we're doing here, we are, and we have this. So this is a good example of what I've talked about in other contexts, and I'll put the. I'm gonna put the paper up. So I've talked about the difference between code that we write for extended methods code, to call it, meaning that this is code that we're writing to do some analysis. We're putting it out there, and we do want to put everything out there for reproducibility. I mean, in this case, this EOS is maybe an extreme version of this, where we are putting everything, all of the intermediate results. And but frankly, it can be a little bit less robust. And this would be the exact example of this is acceptable for this type of code. It would not be acceptable for a tool because here it's possible, right? So let's say you get the code is running, right? This runs here, starts, and now it has to delete 100 files, and it deletes the first 50, and then there's some sort of interruption, some sort of mess up. Now you have an inconsistent state because you're going to have 50 files, so you cannot run the whole thing again. So Jug will be broken. If it tries to run it from scratch, it will fail because half of them are missing, so this can get into a pretty nasty state. We could do this in a much better way, or in a safer way, by splitting this up here, but that it's acceptable that we will have to just rerun these things from scratch. So potentially we'll have to rerun these things from scratch at some point, but for now for code that's really only for internal use, this is fine. Right, all right, so still let's just add a check, so at least this will fail more explicitly, and this is good enough code for this. Let's see now. All right, really? Oh. Okay. Oh, yeah. All right. Okay. I am slowly starting to okay, now it's gonna run. It's gonna take a little bit. Let's see. This is still running. Just to check. Yep. Double check. Okay, there are always 3. It's always 3 tokens, you know? Okay, and I think... Okay, this... Yeah, okay, so this really brought... So this brings down the usage by quite a lot. Just let's just check that everything here is still running as it should. So okay, so this is so this is okay. All right, great. So this is where we were. this is the bit that didn't work before, right? So here, instead of this, yep, no, what did we call it? All gene positions. Okay, perfect. Okay, we can okay, this works, and yep, it's not so slow, but we can probably do this in a single all gene positions or diamond out. Join. Yeah, probably the same thing, right? That was instantaneous. Yeah, all right. Okay, so this is great. All right, so we went for something that was one of the bottlenecks of this process to something that runs in half a second. Well, or basically we have pre-computed everything and saved it in this TSV file. And now we just load it every time. Right. Right, so this check that. Okay. All right, so this is pretty good. Yep, same results as before. Everything is fine. We have just, what did I, oh, okay, I forgot to commit this yesterday, and now, but now. Pre-compute all. Actually, it's not just a refactor, because okay, I think this simplifies everything and makes things faster, and now potentially it will allow us to do things. It will allow us to run on a much larger data set. Right. Okay, so now we do need to start the big computation, right? So in the big computation is we need to expand. We need to expand this. How do we do this, headers? So we could do every single genome here, but I don't want to do that. That's 40,000. So why don't we do something a little bit differently? Why don't we do one why don't we do this? E equals, okay, done. Okay, I think this is a genome ID. Okay. I'm doing something a little bit silly, actually, to be honest. Okay. Because why not? How do I do this? This works. All right. So I'm doing something a little bit silly, which is, all right. So I want to select a random set. So I don't. So, but I want to. So I could do it like this. So import random. If random dot random less than some probability. You know, whatever. Right. The problem is, so every time I would run this, it would give me a different result. So we could set the seed. That would also work, but then if I change computers or any small, this is actually very, very sensitive to what your software stack is, you know, not just what your version of Python, but your version of Python, NumPy, even the underlying system. So instead, we're going to do this thing where we compute this complicated hash, and then we use this as a random number. And then let's select, so if we select 1% of the data, what does that bring us? We never actually finished thing, but I think it was, let's say it was 40,000. So if we do 400, so that's 1%, this would work. Okay. So how are we gonna do this? Let's, okay, something wrong here. Okay. All right, so my system's not working for some reason now. So we're going to do it this way. Except that this is... Okay, we're going to do this way. All right, so this will select every 100th or every nth, you know, to be honest, or to be precise, every nth genome. And so token yep. Sorry, let me we have atrociously bad internet around here. See, this is okay. I'm gonna check so I'm gonna so this checks that we have only gotten the wait a minute. Okay, let's do it this way. Okay, so this checks that we have gotten. Right, we don't need the headers. Okay. So if everything works okay, so this will go over the representatives and then create the expanded set. So actually we need to make the earslet there. We create the expanded set for every 100 in this sort of random way, but it's a random deterministic way, which means that if you run it on your computer, you will get the exact same results as I do. Okay, return. Okay, and something like this should work, right? We got the so here this code assumes that the that the representative genomes are, grouped in the FASTA file. I'm not 100% sure it's correct, so this might, if this fails, we'll have to add a little bit more code, but otherwise this should just expand. So let me okay. Okay, so far nothing. Okay, it's possible that it just happens that the first few are ignored. So something's running. Oh, there it is. Potentially this should have been. Yeah, this should have been compressed. So let's just make sure that we can. Yeah, this should. This is not. Yeah. It's not ideal. We should be closing the files, etc. Again, this will work just fine for this. So now we're JZipping. So I always like to JZip files for two reasons. So maybe the first one is pretty obvious, is that it uses less disk space. Disk space has gotten cheaper, but it's still not free. But the other reason, which in some ways is more important, is that it adds checksumming. So if the files get corrupted in any way, JZip will generally catch it, 99.999% of the time. And you might ask, oh, well, how often do files get corrupted? Actually, they get corrupted if there's a very specific way in which they actually very, very often you end up with corrupted files, which is you have a partial file, right? If you have, interrupted transfer, something's running and then you just, oops, okay. And I should not be talking in. Right, but by the way, you can see, I don't know if you noticed, this might have been a bit too fast, but you can see that this was, it generates always the same file. So this file here, it's the same because it's randomly choosing the same things over and over again. But what I was saying before about JZipping is that you have this checksum, and it's very, very common that you have these interrupted partial files. And in some file formats, that's very easy to detect, but in others, and in particular, text-based formats and FASTA files are the worst. So it's very, very easy to, if you have a FASTA file, if you're interrupted, unless somehow you got interrupted in the header, and even then, it's not clear that maybe you just have a short header, because you can have a short header and you can have an empty sequence, and that's still a legal FASTA file. But if you have something that's interrupted in the middle of a sequence, you might not even know that you were supposed to have 15 contigs and you only have 8, and the last one is you only have half of it, and so you end up with half of a genome and you just don't see it, and then all of your results, they look perfectly fine, except you have you have bad data there. And this can happen so easily, and then if you have JZip files, this problem completely goes away. All right, so now, this will run, but obviously, okay, let's remove that. Obviously, this is not going to run on the stream. So we're running now for a minute or so that I've been talking, and as I said, this this is random, but we probability about 1 in 100. There's 40,000, so that's going to be 400. I've been talking for a minute or so. We've done 4, so it has to take a couple of hours. But so we're not going to finish that today. But let's instead actually, let's do something a little bit sneaky. Something a little bit sneaky. Okay, okay, this is a bad idea. Don't do this at home, kids. But okay, this is gonna pretend finish, and it will maybe allow us to do it. So instead of but it will maybe allow us to just oops, did I? Okay. Okay. Yeah, okay. Okay, well, all right. Okay, all right, maybe okay, all right, so actually maybe we need, let's, okay. Okay, I'm really trying to finish this. Okay, let's have this as the tag. And I actually think this would work. Okay, I think this works. I rushed a bit this ending. Right, so we've expanded all of the progenomes, or the code, wrote the code to do it. And then, instead of this, we would do it this way. We would do it this way, right? And now, the only thing I don't like is we removed some code that I now realize probably this get gene sizes. I'm a little bit annoyed because we're running out of time and I don't have, so let's, okay. Okay, let's just call it a day here. I think we've made a lot of progress. I think that this get gene positions partly overlaps with this idea of calling prodigal again, which was probably a bad idea anyway. This was bad. I will double check this next week. I would need, well, no, let's just double check it now. Okay, so I'm going to stash the code, or stash what we did. And just shell gene sizes. E. coli. Is it E. coli or like this? E. coli. Okay, we're gonna E. coli K12. Okay. 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 Now I want to do S filter number of mutations. Select length. To numpy. And I will copy. Oh, very nice actually. Very nice. Very nice because we found a little bug. Very nice. Very, very nice. Okay. All right. So this is very nice. I mean, it's also valid. So I was thinking, okay, maybe I should just delete that code. It seems reasonable. And everything. This code was silly. That was doing, it was doing a lot of computation that was done anyway through this. Right. So I'm going to show you. So this is the. So this is what it was doing. So it was running prodigal, calling prodigal again, some sort of weird thing and then loading all of the genes and then just counting, getting the gene sizes, right? And this was doing the exact same thing that we now do by parsing the headers. So it should give us the exact same result. Alas, it's off by 1. Why? Because our code is wrong, right? So now it's very, very nice. Very, very nice. Okay, I'm gonna do this. So this prodigal gene sizes, this is all wrong. Oh, this is not all wrong. This is, yeah, gene positions. Yeah, this is, yeah, let's do the position like this. Okay. Oh, okay, now it's not gonna work because, yes, okay, fine. Fine, but prodigal coordinates are inclusive. So, all right, so this, now, all right, now we can remove all of this. Now this will work. This will, okay, I'm gonna, no, I'm gonna keep it, let's keep it. All right, okay, all right, so this will take a while to run. Okay. Use. Okay. All right. Let's just add some nodes. Today is the 18. Okay, so this we have kind of done. So in it, all right, so we cleaned up code, cleaned up intermediate, cleaned up code. So we did, and then see, save fewer intermediate files. Enable scaling up. Okay, so we actually, it's not even to test the pipeline, just add notes. Okay, so I did, all right, summarize. Okay, so okay, now I'm also going to start running this, and then maybe if things go okay, if things are okay, I'll show the results on the recap, and obviously also next time. So as always, everything is on the GitHub. So I'm actually just going to push to the GitHub right now. 1, 2, 3. It's push to the GitHub. So we went slightly over time this week, so I do apologize for that. But I will see you next week. You know, do subscribe to the mailing list as well. I'll post some of the updates later, and so I'll see you next week.